What we plan to do here is to create a model of a sine wave using Keras sequential model. Keras has another model type also called functional model. This is a sequential model. I talk about what it is and how do we use it. Mostly whatever we use is a sequential model only in our practice things. Then I will explain a little bit about, you must be knowing most of the things. What is the rectified linear unit activation function? What does it do? What is the benefit of them? And then how does the Keras differ in terms of learning or training the network compared to TensorFlow? So one thing I want to clarify, see, if you are looking for Keras library, it will look for Keras not from Keras.TensorFlow. Okay, in that case Keras is on the top and TensorFlow is down, but actually TensorFlow.Keras. So what they have done is Keras API, one Google engineer, he has developed seeing the difficulties that people face in using the TensorFlow, especially the 1.0, and he has developed some APIs which make use of remove some difficulties that we had in TensorFlow. And by the time 2.0 also came, TF, then Keras APIs became part of the TensorFlow 2.0. Okay, so that's why we see that TensorFlow.Keras will say, but in reality, who came first is like a egg or chicken. TensorFlow came first and then Keras came next. But because of the simplicity and the usage, Keras got into the TensorFlow and they included it also as part of the TensorFlow release, especially from 2.0 release. Okay, that's one clarification. You may be needing that. Okay, so now let us look at the way we will build the sine wave, and we'll play around with that. Hopefully Jupyter should be able to help us in running it, because now just before the class I closed the spider and started and it notebook vanished. Okay, no problem. Let us look at the sine wave generation. Before that, what is a sequential model in Keras? There is a type of models that you can create. It actually, the Keras API documentation says that this layer has exactly one input tensor and one output tensor, but it is not really true. They also tell in the documentation that a non-sequential or a functional Keras model is one which does not have either multiple input tensors or either multiple output tensors. That means they are not sequential, they are non-sequential. Okay, if one of them have multiple input and multiple output. So in our sine wave, whatever we are trying to generate sequential model, this condition is not satisfied fully. That means actually it is each neuron is going to take multiple inputs, but it will give you at the neuron level, not at the layer level. Layer level, multiple outputs are coming. From this layer, multiple outputs are coming. At this layer, multiple inputs are also coming. But we still call it as a sequential model. Okay, the definition says that is single input and single output tensor, but we are also, maybe it is generalized, or I'm not sure very clearly what the definition is. I couldn't find the proper definition for the sequential model. But one thing is clear, that sequential model is something which is having layers one after the other in a sequence, and there are no we don't form a layer out and then take something out of it. Okay, first of all, this is a feed forward network and sequential in nature. So these are all the definitions which actually matches with what the sequential model they claim it to be. Okay, so that is the one definition. It's not actually single input or single output tensor. Okay, it has a multiple input and a multiple output tensor at the layer level. Okay, now you can create a sequential model by passing a list of layers. Now how do you create it? It is actually simple to create. We can either pass all the layers and create one sequential model in one go, or we can keep adding it to that layer by layer. Okay, and when you are adding it, it will always add one after the other. So that is also one of the reason that you can call it as a sequential model. Because suppose if you have a add, if you call with maybe 10 nodes, and then you call add with the 20 nodes, 10 nodes will be here and 20 nodes will be here. Okay, so normally what will happen is it will be expanding and then shrinking. So this is how the normal layers form. Okay, add means it will add next to the previously existing layer in the model. So you can also create a sequential model incrementally by adding method. There is also corresponding pop method to remove it. I have not tried it out, but for a completeness sake, I have given it. Maybe you can try it out. Then layers in Keras need to know the shape of their inputs. Now let us see. Now suppose you have a neurons, multiple neurons. You have created the one particular layer. You mentioned that it is a 10 nodes. You want 10 nodes to be there. Okay, in our case, I am showing only 5 nodes. So let us call it as a 5 nodes. And then you also have another option to say whether it is a dense layer or not. When you say dense, what happens is whatever is the previous layer, from all the nodes of the previous layer, all the outputs, each of them are giving one output. Each node is giving one output. All the outputs of the previous layer go to all other nodes of the next layer. So that is what is called a dense connection. You connect everything to everything else. So that is one thing you should remember. Next is, now how does it know what is the input coming in? One thing is the model is generated which is generic enough. As I said, even tensors also is a dynamic in nature. If you recall dynamic typing. So static type and dynamic in terms of size. Okay. So because the tensors also like that, even the model that we create also can accept any type of input. So based on the input, it computes the weights. Okay. So when you create a model layer by layer, it still doesn't know what is the type of input expected, whether it is a one dimensional array or two dimensional array, or n what is the n dimensional input which is coming in, it doesn't know. Now based on the input, it may have to create the weights, because it has to do a arithmetic with the weights and the input. So when the model is created and the first time you are feeding some data, based on the type of the data that comes in, the model understands that that is the input it is supposed to get. So it creates the weights for the first time. So after that, it knows that okay, that is the input that is coming, so it will start doing it. So for every node, for every input, there will be a weight associated with that. And if you are having 4 inputs coming, then 4 weights will be there. And for each node, there will be only one bias. Okay. So there will be one bias which is normally not shown in the pictures. Don't assume that it is not there. It is there. Only the connections are shown normally. But even if this is in terms of millions of nodes, you will not be able to even show them. So always, as you know, remember that every node has a bias associated with that, and single input. There is only one bias, which is just coming in from nowhere. It is not coming from the previous layer or something. It is a separate array initialized with some values. But when it is computing during the back propagation, when it is computing the bias and the weights of the input by doing the gradient computation, it is updated. Okay, all the things are updated when the propagation happens. So during the input, one input based on the epochs we have decided. Okay, so only when you have decided that okay, for all input epoch is equal to 1, then every input the weights will be computed. But if you say that epoch is some 10 and then batch size is something else, another input that we give, that is what happens is during the batch size, suppose you are given batch sizes at 10 inputs will be given one after the other, because we are normally giving an array of inputs and we say what is the batch size and what is the epoch. So if you say batch size is 10, that means after 10 inputs have been processed, then the computation of weights and back propagation happens. Now based on the number of epochs you give, it will be done multiple times. So let me explain it again. Okay, suppose you have 100 inputs. 100 inputs you are giving, and then you assume that this is the output layer, this is the input layer, and there are in one layer which is four nodes are there. Now what happens is we have given 10 as a batch size and epochs as 100. That means what? I give out of 100 inputs, I give 10 inputs. Okay, and then we do not, during the 10 inputs, the weight and then back propagation doesn't happen. The weights and base biases are remaining same, whatever you initially set up with, and then epoch kicks in. That is after the 10, you have to first epoch is done. During this epoch, what happens is it whatever is the output taken, it knows loss function is given for the whole tree. There is a loss function is there. So based on the loss function, it will know that this is the output coming, but expected output is something because it knows which input has come, and then it starts computing the weights and biases, and that gets propagated up and updated. And then again batch of 10 will be given without calculating the back propagation, doesn't happen during that time. Now after 100 times, that means you weight and biases are changed, and then loss function will have a different value now because you have modified these values. So when it comes out again during the next epoch, the loss function value will be different, and then it will go around again modifying the values. So this is called actually optimization, because it is trying to optimize the inputs of the controlling parameters of each node to get what it wants at the output. Okay, if it wants the particular output here, that means that it needs some inputs to be given, which have nothing but the output from the previous layers. So then it goes on computing what should I set this weight as, what biases, and what should I set the weights of this input as, so that I get what I want. So this is how it goes and propagates back. And during the computation, it needs to know whether to increase it or decrease it. So it computes the gradient, because loss function only gives you whether it's where you're looking for a minimum value or maximum value. Based on that loss function, you need to consider it differently. So the model will try to update the weights and the biases based on what it wants to achieve as a loss function. What is the output, whether you want to minimize it or maximize it, then it will go on modifying the values. So that is how this thing happen. And the back propagation part of evaluation is called optimization. That's why in Keras it is called optimizer. So whereas in our TF we used it as a gradient tape, where this optimization job was done. In Keras we call it as optimizer, and we also give what is the loss function and what is the transition function. Each function is having the function which is defined. Now either it is a sigmoid or ReLU function, we will be using it while doing the computation. Okay, I will anyway give you the background of this also. So Keras need to know the shape of their inputs. That will come to know when it first gets the first input. Then when we instantiate the sequential model without an input shape, is it not built? It is not fully built. The model is not fully built, and it has no weights. Only when the first input it sees, then the weights are built and the model is completely built. And there is a function called API, which is called summary, which gives you the summary of all the parameters and which are configurable, or which I will talk about that, okay, when we run it. So we will see that. Okay, this is the crux of what is the sequential model is all about. Now, how do we construct a neuron, one single neuron? So as I mentioned, all the inputs are multiplied by the weights, which are nothing but the input coming from the previous layer, which is nothing but the output from different nodes of previous layer. Okay, now they are getting multiplied by W, and they get added sigma, and then bias also added. Now bias is only one value per node. whereas weights can be multiple based on the number of inputs that it gets. And then the activation function is acted upon. So activation function is after the sum of input and output, then bias of particular layer, and on this value the activation function works. So if activation function is f of x, the output is y. Now we decide the activation function based on some criteria that we will be mentioning it when we are creating a layer in Keras. So each neuron in the network will be fed by the input tensors. Again, all of them are tensors only, nothing else. And each input coming into a neuron is multiplied by an associated weight. Then each neuron would also have an associated bias. The summation of weights input is added with the bias before applying the activation function. So bias is also added along with the weighted inputs, and then the activation function is applied on it to find out the value of output. That will be the input for the next layer. Okay, now model construction. Now how do you construct it using Keras? So we call it as a sequential. So here we are only just created the template. We are not even mentioned how many layers they have in this case. Then we say model 1 add layers, and we say dense. We want these layers to have a dense inputs. That means whatever is the previous layers you have, previous layer, how many nodes you have, from all the nodes I want the input to be given. Now in our case, when we do just a sequential, there is only one node which is an input node, because here it talks about only one input node. And then we say that I want a dense layer of 16 nodes, and activation function for each of them is ReLU. So we are saying each of them are ReLU. We need 16 nodes, and the input shape we say that is at single dimension. Okay, in this case we are also mentioning what is the input shape of the node or the layer for this particular layer. And then we do not mention that this is a single node. Okay, it is implicit based on the input type what you get. It's a single node, and then it feeds whatever is the, here there is no ReLU function or anything. Whatever is the input is given is fed to it. So all of them, the same input goes to all the layers. So that is this particular layer talks about. And then we say add another layer with dense 1. Then what we do, we are saying that I want only one layer, but I want, one node, only one node, but I want this to be dense again. That means what? I want all the outputs from all the previous layer node should be fed to it. So the output node is also dense. That means this many are coming in. And then we say there is no ReLU function here. So here there is no ReLU. We don't have an activation function. Whatever is the some value of this will be given out. Now this also has a bias. So each of them having a bias which is not shown in the picture. Now I want you to calculate how many parameters are there in this case, configurable, which can be updated on every iteration or every epoch when the learning happens. How many are going to be there? Now let us assume now this is all 16, right? 16 are, because 16 nodes are there, that means we have only 16 inputs. That means there will be 16 weights also. Each of them will be having 16 weights. Okay, and then here we have dense, here we will have 16. Okay, now how many bias you will have? Here there will be 16 biases. Okay, and then we have one input, only one, 16 here, 16 biases here, and then here how many you will have? Because 16 nodes are there, you will have 16 weights and then one bias. So you can calculate how many will be there. Okay, now I will leave it to you, you can think about it. Now what is the input? We are having sine x, we want sine x. So x has to be some radian in radians. So that should be 0 to 2 pi. So that should be the output. And then why we want it to be within the range -1 to +1, because sine wave is always 0. This is 1, sorry, 1, this is -1. And the values are 0 to 2 pi. And then it starts repeating. So what do? We give input by taking different samples here. Suppose if you decide that I want 1000 samples to be given, I divide the 2 pi value into 1000 small instances, and we'll add some noise to it. So we'll give that as an input to the actual network. Similarly, we will also get an actual value for all the inputs that we give. And we have a y here, actual value, which is coming from the sine function of numpy. And then we have a predictor value coming out of our node. And then we'll start number of epochs we will decide. Then we start learning, or we make the our model to learn. We don't learn, the model is learning. Okay, that's a summary of what is happening in this. Okay, this is how we are initially building a node, not a node, network. Okay, now 16 nodes, input node, output node. Each input has 16 associated weights. Each node has 16 associated biases, and we have each input has an associated weight and one bias, because there is only one bias coming, and then we have 16 weights here. So you can add up everything, it will be 49. Okay, so how many parameters which are configurable? There are 49 parameters which can be learned or configured to get the output that we need. Okay, I hope this is clear. Now I am showing you little more. This you have already seen, building the network. Then optimizer. Now we are mentioning the optimizer is nothing but, as I mentioned, it is a gradient. Okay, gradient computation, but we are not doing a the normal gradient that we learned in TF. Little different from that. It's called RMS prop. I will talk about it soon. And loss function is same as what we said earlier, MSE only. And metrics is something which you can use it actually for studying about your network, whether it is behaving properly, where you want to debug it. This metrics you can use it. For metrics we are using the MAE, not MSE. And then summary is actually going to give you how many things are there, nodes and configurable parameters are there after you build everything, because you already mentioned about what other things are needed. You mentioned about the activation function, input shape, everything is given. So this is the output. So what does it mean? It has a 16 nodes there, 16 inputs. Okay, this is the output shape. Okay, output shape. And see, this is I think this is given null because of the input is based on the input type. Okay, whatever you are getting, your one dimension you give, but actually it will be known when you have actually when you feed the input. That's why it is printing like this. And then 32 is 16 weights that are coming in, because it's a dense connection. For each node is having 16 inputs, so you have that many weights. Yeah, that is yeah, correct. Okay, sorry, I'm sorry. Each input is having only one input. Okay, because we are not I had another node, so I am confusing you, sorry. So this is the input node, only one input is coming here. Okay, and then there is only one output is going. Okay, in this case it is actually perfect sequential model, because one input tensor and one output tensor per neuron. But per layer, if you see, there are multiple inputs and multiple output. Anyway, that will be true, because in a layer there will be multiple nodes. So we cannot say that I have a layer of nodes, but there is only one input. It's not even practical. So at the neuron level, there is one input tensor and one output tensor in this case. But once you add one more, it will become really dense and multiple inputs will come. Okay, so I am trying a simplest node right now, the network, which is having only one layer in between the input and output, and they are 16, and one input and one output going out. So How many parameters? 49 totally trainable parameter. That means these parameters are taking part in the training. So what happens is when you do a back propagation, the optimization happens, all these 49 parameters will get changed. That's what it means. Okay. And this is the output that you get for the summary when you say model summary. Okay. So I hope this is clear. In between, let me just sample out. Let me see if there are any questions so far. Okay. Okay. I didn't understand how the bias is added to the weights. No, it's not added to the weight. I'm sorry. Oh, sorry. Okay. See, one node is there. Input. Okay, let us assume that for simplicity, we'll assume only one input node, three middle layers, three nodes in this, and then we have output going out. This is the output node, this is the input node. Now, whatever is the input you give, the vector of input, one by one we will be feeding. Okay, one scalar value will be fed to it because it takes one dimensional vector, but while training we will not jump everything, we dump one input. So when you do sin x, we want to compute one scalar value we give and then compute the y value, right? So we want to see how this network behaves when I give one input to it. It's a regression model. It is predicting the output, which is a continuous output which is getting predicted. So to start with, each of the bias values and the weight values, each of them are having some weight values. Okay, these are the values. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In this case, 10 are the parameters which are trainable. Now, bias is always 1 per node. 1 per node. It is not getting multiplied with the weights. It is getting added to the weights and input multiplication. So this is, suppose you have I equal to 0 to 1 to n. Suppose n inputs are there, you give, I call it as x. X is normally given as input, so xi into wi. Assume that now 1 1 1 2 will come. Okay, here we are having only this is w1, this is w2, w3, and this is actually y from here, but it will be an x for this node. So let me call it as x1. Same value will come out. Okay, all, because don't think that 3 are there, then whatever is the output is divided and given to each. No, the same output value computed by this node is given to the same copy, is given to all of them. So they all get the same output coming from there, but the differentiation is made by multiplying with the different weights. So sum of xi and wi plus by bi or b, whatever is the b0 or b1, b2, b3. So individually these biases are added and the total value is given to the activation function. So activation function maps that value to something else. So there is a mapping happening during the activation function, and then the output is generated. So this output, if it has to feed to multiple nodes, it will give the same output that it has computed. Otherwise, if it is only one it is connected to, it is the same output will go out. I hope this is clear. Devashish, I didn't understand how the bias. Okay. You can use notebook from Spider by enabling it from view pane. Oh. Okay. I want to actually go back to Spider. How did I enable?
In pens you go.
Thanks, man. I did once, I forgot. My memory is 1-bit memory. Thank you. We're doing something. Okay, let me, sorry for the interruption. I want to see whether it works fine or not. Sample program, Keras. Something is really wrong with my. Okay. Good. Thank you. Who said that? I didn't see. I can't make out the voice. Who?
For me, man.
Okay, my uncle. Okay, thank you. Oh, here it is there. No, okay, sorry. Okay, got it. Fine. Now let me go back where I am. Please ask me if you don't follow anything so far because this is very important for you to know. Now I say ReLU here. So what is ReLU? It's a rectified linear unit. A simple function, a linear, this is linear line with a slope as 1. So whatever is the input is the same as output. So if I ask you one question here, I mentioned sine wave is what? Sine wave is actually varying from -1 to +1. We also saw in the diagram saying that output is between -1 to +1. Okay, that means what? The output layer, after all this business done, in our case, this is going to give you some negative value for some values of x, right? It is going to be y is going to be some negative value, but we are applying a ReLU here on all of them. All the nodes are operating on ReLU as an activation function. That means what? Whatever is the input I give, whatever is input, anyway input is 0 to 2 pi, which is nothing but some positive value only, is not negative because we are only giving from 0 to something. So it is going to be positive value. And weights, we don't know. Weights can be positive or negative. Okay. Similarly, bias can be positive or negative. Okay. So weight can be positive or negative. Bias can be positive or negative at each level. And inputs are going to be positive number 0 to 2 pi. Then what do you expect the output to be? That is the output of these nodes, which I call it as y1, y2, y3. Will it be anywhere? Will it be negative at all? Can it be negative? Can somebody answer? Or I need to see there? No, I don't want to discard this. Keep. Okay. So anybody can answer my question. Can the y be negative at all?
Sir, is why the layers, the previous layers output or the input to the final layer?
It is same. Please remember, output of the previous layer is the input to the next layer. The same line. So y1 is maybe taken as a x1 for this guy. Okay, but they are same. Y1 is same as x1. There is no transition happening, but after that weight will be multiplied, but the value what is passing through the line is a tensor which is same. Will it be positive or negative? Can it be both?
After ReLU, it cannot be negative, sir.
Very good. So after ReLU, because if you recall, I said that sigma plus bias is acted upon by the ReLU. So ReLU is doing what? It removes off all the negative values. See, if you see that this function is actually makes the negative value 0 and all the positive values it sends it out untouched. So you may wonder, how do I get a negative value here? Can I, first of all, after the transition you are not going to get it, but after you perform this job of multiplying the x input and the weight and then adding the bias, can I have a negative number? Yes, very much you can have, because you are not deciding the weight here. It is decided by the optimizer. Maybe initially you will give some random value which could be positive or negative, but after that it is getting modified by the optimizer. I am going to use optimizer now, which is nothing but the gradient. And the bias also you give initially some value, but it will be fine-tuned by the optimizer. So they are getting changed. You don't have any control on whether it is going to be positive or negative. But after the training is done and you give an input, when it finally again comes here, it will be output is y is going to be positive only, because we are applying a ReLU as an activation function. Now my question to you is, if all the inputs to the output layer, in our case, in this specific sine wave case, if all the inputs are going to be positive, on what basis we assume the negative thing is also going to be generated by this guy? How do you say that we are going to get a negative value coming out of this fellow? Can you tell me how is it possible? There is no ReLU here. Okay, please remember there is no ReLU here. So it is not going to make any negative value again to positive. Okay, first of all, input itself, we have seen that if ReLU is operating here, all of them are going to be input is negative, sorry, input is positive, but it is going to be multiplied by weight. So after that it can become negative. Okay, please remember what is coming first. Output is coming here, but before feeding it is getting multiplied by input and then coming. Okay, so there is a little difference between this one. Okay, what is finally going into it is multiplied by the weight, but the input is called as xi, same as y. Okay, that is not, there is no change, because that's like a single line, like a current passing through that. So the same tensor is here and same tensor will land here, but after it comes here it is getting multiplied anyway by weight and then getting added with all of them, so it can become negative that time. Okay, because weights can be positive or negative. So even though the value is tensor is what is coming could be a positive value only, but it can still become a negative. But after addition it can be still negative because of this weights being negative, as well as the bias. When you add a bias, okay, when you add a bias, after the summation is done, you are adding a bias. Now if bias happens to be negative and the summation happens to be lower than this negative bias, then still output can be negative. So still it is possible to have half of the values as negative if the input is distributed. Okay, I hope you understand how finally you get a negative value at the output. Okay, now I said I want to retain it, so it is gone. Oh my god, I have to open it again. Don't save. I hope that is clear to you. Let me see, having come out, any questions are there? Okay, fine. Now where is it? Where are we? ReLU is done. Oh, so not done fully. Okay, now let us understand it. ReLU better is the most commonly used activation function in CNN and is nothing but a max of 0, x. So you can understand that any negative value, if x takes it, it will be lower than 0, so 0 will come out. So it is very obvious. It's a linear identity because it's mapping all the positive value in a linear way, and even though the total function is non-linear, it is piecewise linear, as I mentioned earlier. Between 0 to all negative infinity it is linear, and 0 to all positive infinity is linear, but overall this function is a non-linear function. Don't think that ReLU is a linear function. It's not. Okay, it's not behaving the same way. It behaves like a more or less like a diode characteristics. So linearity means that the slope doesn't plateau or saturate when x gets larger. So if you might have seen the sigmoid function, which happens to be I'm not drawing properly. Oh, I cannot erase it. So sigmoid function changes from it is like this. It is 0.5 here, 0 here, 1 here, and for during some gap it is in between values can come, and then it plateaus to 0. Whatever is the value of this, 0, and whatever is the value here is 1. So that kind of truncating it to some value which is sigmoid is not with the ReLU function. ReLU function is 0 here, but all positive values it gives out without any distortion. So it gives you, and it can go to any level. Okay, this you keep in mind, which is helpful for you to understand. the next line. It does not, the ReLU does not have the vanishing gradient problem. So this is nothing but a gradient slope, and it doesn't vanish. Okay, in a sigmoid function, it vanishes if the gradient is more than 1. It stabilizes as 1 in sigmoid, but here it goes on. So there is no vanishing gradient problem, which is a very famous problem in the neural network, wherein some gradient values in the network, after having learned, it gets vanished because of the activation function what you have chosen. If it is not a ReLU, this problem will be there. But it's not that I'm saying that sigmoid is bad. It will be useful for something. And this is a tan h is another function which could be used, which is non-linear function and doesn't have problem like, it's not similar to our ReLU. And one more advantage of ReLU is it converges faster. And okay, why is it converging faster? Let me also tell you. When most of the, okay, suppose if you assume that probability wise whatever input you are getting is half of it is positive and half of it is negative as an input, not even input, whatever you compute, okay, whatever you compute after the bias to give it as an input to the activation function, if maybe half of the input may be negative and maybe half of the time it will be positive. So those half of the values will be made as 0. Now once some output of a node is 0, it actually simplifies the down path, because you don't need to do much with a 0. You don't have to multiply with a 0, right? Weight multiplication with the 0 is not needed. So some of the hardware, especially the AI hardware, which are helpful in building neural networks, like our NVIDIA's GPU or something, they actually take advantage of this values becoming 0. That means suppose you have a memory and then you have a AI machine which is operating, and then it has to read the values of weights and then different inputs that are coming. It will be written into this and then maybe read from this for the network to run. If it happens to be 0, some optimization is done that even it will not wait for the transfer of 0 values from here to the AI machine. So they avoid spending energy in transferring the 0 value into the input, because 0 can be recreated internally by the machine. Okay, it is like a reset. If you give to the flip-flop, it becomes 0, right? So if you have the 32-bit value, if you want to create a 0, there will be standard registers also with some of the CPUs will have a register with all values 0, so which will be loaded internally. It doesn't have to take it from the memory. So transfer of a value which is 0 need not be taken from the memory to come into the machine to perform the remaining operation. It can be recreated internally as long as it knows that a particular value is 0. Okay, so some optimizations can be done when you have a network with lots of 0 values percolating inside the network. So that's one thing we should remember and see. It helps in terms of making your network run faster and execute faster in terms of performance. That is why ReLU is converges faster, as well as it is easy to compute. You don't need to do any mathematical operation. Max operation is very simple operation you can do. Comparison operation is enough to say that it is a positive or negative. In fact, you don't need to even compare. If you have read about IEEE 754 that I gave you, or if you have read somewhere, or the 2's complement representation of negative value, the MSB bit 1 means it is a negative value. Okay, so just checking the sign bit of the value, or the MSB bit of the even floating point also. Even the floating point has the same convention of a negative value being represented as a 1 here. Sign bit is reserved as a MSB bit of either 32-bit, 64-bit float or double. So you can just check this bit and then decide about it. Okay, whether to give 0 or the same value. So such a simple operation the ReLU is. So if someone asks you, how do you say that ReLU is faster and how is it computation is simple, you can just explain this much. They will just blow out of, they'll think that, okay, internally what is happening. So negative values, it has to be suppressed as a 0 and positive value is taken as it is. So there is no computation actually involved. There is no mathematical computation involved. That is why it is very fast. And another advantage is sparsely activated ReLU. So in probability wise, you can see that some maximum value can be negative. I'm not saying that always 0.5 because it depends on the data you have and the model you are trying to build and what type of input you are expecting. Whether negative values are not even expected at all, then you are not going to get any benefit out of it. Okay, don't generalize it. But if the input happens to be having so many negative values and the network is having lots of negative values also, and if you use ReLU, okay, we have to be very careful when to use ReLU or not. But you are going to have some relief if the network is sparsely activated. That means 0 output means it is not activated. It's not fired. Okay, that network is, that particular node is not fired. So you don't need to do any operation for that. My weight multiplication is not there, addition is not there, and bias can be just taken. Lot of input, advantages are there. So a sparse network is faster than a dense network. Sparse in the sense, I'm not talking about the connectivity in the network. I'm talking about the data flowing through the network. And if it is a sparse means the data, most of the data flowing in the network is 0. Okay, then it is sparse. Then you need to have fewer things to compute. So I hope ReLU is clear to you now. Okay, you actually refer all these links I'm giving you. You will actually read more. I find the best the article on each of those things and give you here. It's like I have done lots of work to finally find out which is the best explanation. So I'm not saying that all the links are perfect in their content, but it is well explained and very nice. So if you look at all the links, in fact, whatever I have missed out, or if I have misread something and misrepresented something also, you can catch and let me know. Okay, so please read through all the links that I give you. And then finally optimizer. This is where what is happening after giving one input. When the epoch is starting, you need to optimize the network. This optimizer is going to be called. So you are compiling it and making it ready. So here we are giving what function to use. Optimizer, RMS prop is the function, and the loss function is also important because based on the loss only we are going to compute the weights and the bias. So optimizer is responsible for performing the gradient descent algorithm for computing the weights and biases. This is similar to the gradient descent algorithm with learning momentum. So if you have not heard about it earlier, learning rate we are not mentioning here. Okay, that's why I initially did the TF only to differentiate between what we do in Keras and what we don't do. What we do in TensorFlow and what we don't do in Keras. We don't do a configurability. We don't have, or maybe there may be some other mechanism to do it, but we don't give, at least in this case, I am not giving any learning rate at all. Now, how does it decide what is the learning rate? Okay, because you know how important it is, because we fine-tune the learning rate to actually get the output that we wanted in the last class. So learning rate is important, but we are not giving it here. That doesn't mean that it doesn't use the learning rate. It uses internally. Change in rate is momentum, you know that. So change of learning rate is momentum, and there are two different ways of changing the learning rate that internally RMS prop does it. So if suppose your value, that loss value that you are computed, and then the gradient that your next value you will compute, if they are of changing like this, okay, that means it's like a random walk I mentioned. Okay, if suppose you have a loss function which is like this, you may get caught here. So if you are coming like this slowly, learning rate is slowly coming, you may come here and then get caught here. You will never come to the local minima. But if you have a faster big learning rate, then what happens is you may wonder how is it transferring from this point to this point. When I say learning rate is bigger, see, we compute, not you, we compute the gradient descent or whatever algorithm is computing the slope, and then it is going to update the weights. So it is, if the learning rate is high, whatever is the updation it is going to do, it is going to do a bigger change. Okay, it is going to make a bigger change based on whatever error it has computed, it is going to make a bigger change to the coefficient. So when the next input is given, because we are assuming something else, okay, the model is something else, but we are assuming something different, because learning rate is big and we gave a big changes to the weights and the bias. What happens is it lands here, the value what you for the input what you give, okay, the output is nothing but the after the weight is multiplied and then the bias is added, right? So we are not actually taking the original input that we got, we are modifying it. So it jumps because of the reason that learning rate is high. We modify the weights and bias so much based on one error we compute, and maybe it's a mean of error, that is okay, but still it is big enough for us to jump to something else. It may go up or it may come down. So in this way you can keep shuttling between this, avoiding the local minima. So that is the reason this guy for a law, okay, that's a different learning rate it uses based on the changes that it sees. If it is a learning rate is bigger, sorry, it does horizontal changes, means if the values are jumping from one area to the other area, it does a bigger learning rate. But if it is in a smaller learning rate, it uses when it is vertically changing, okay, because it has a three-dimensional view of the actual loss function, okay, so it can find out. So RMS prop optimizer restricts the oscillations in the vertical direction, whereas allowing larger changes in the horizontal direction. Please remember, you should not allow bigger learning rate in the vertical direction, because it may be worst thing may happen. It may go here or it may miss something, okay. So it should be coming closer so that it doesn't miss the minima, but it can jump in the horizontal direction large, because most likely it is going to be beneficial for the network, okay. Therefore we can increase our learning rate and our algorithm could take larger steps in the horizontal direction. So that is why it is faster. The convergence is faster because of this particular change, okay. Normally what we do in TF, you will not see it. It will be much better when you do it in Keras with the RMS prop optimizer, okay. That's a understanding you should have. So horizontal rate is higher to avoid getting caught in local minima. This is the reason we don't mention any learning rate ourselves. It decided dynamically by the Keras model to make the model converge faster. I hope this is clear. This is most important thing we should know. Now I am going to show you the input that we are going to give, and then we will divide the training and validation and test data, and then these are all different colors you are showing. I'm giving you those input, okay. It is without too much of noise here, and then with the 16 nodes, this is the model output, okay. Do you call it as a sine wave? You don't, but we will see how to improve it without changing the too much about the model, but we have to make some change, okay. Fine. Now I will stop here before going to the code. What I will do, I will give you the code now, and then I will take some 2 minutes break. Okay, we'll take 5 minutes break. I will share the code. You can also set it up and we can meet, okay. So 7:10, okay, what is the time? 15, we can meet at 15 also, okay. Sorry, 5:15. Sample prop. I hope this is what I'm running. Yeah. Hello guys, could you run the code? Is it running? Hello. Okay. So will you be looking at the screen or you are looking at the code? I don't know. Your own code. Please just spend some time on my screen. I will explain quickly and then we can wind it up fast. Okay. Not that we need to take all 2 hours. If you understand the code, I think I have explained most of the things. So we will just quickly go through it. This all you know. That's what I said. TensorFlow inside that Keras is there. So it's not Keras is using TensorFlow. It's the other way around. TensorFlow is using Keras. So the reason that Keras is using the TensorFlow API, they have bundled it as a one of the packages of TensorFlow. So it has come inside that. Now we are having 1000 samples. That means X value, which is between 0 to 2 pi, we will make it 1000 values we will get. Okay, we'll see how to compute it. Then we have a seed. I hope you are all aware of this, where you use the seed. What happens in a cryptography or any random number generator that we have, a random number generator, RND, the algorithm has the seed as an input, and then there is a fixed algorithm which does some mathematical operations or logical operations on top of it and then convert it into some random number. Now this number, random number, is called pseudo random number when we started with the seed, and when we say it's a pseudo random number, that means it's a random in nature, in that suppose it is generating some x1, x2, x3. These values, whatever is coming out, they are random in nature, but it is decided by the seed that we give it to the function algorithm. So if I give seed 1 and then I get x1, x2, x3 values, specific values, or maybe let me call it as n1, n2, n3 values, then every time I run this algorithm with the same seed 1, I am going to get the same sequence. In the sense, the first value will be n1, the next time when I call random, it will be n2, n3, n4. That is called pseudo random. It's not really purely random, because in every run you are not going to get the same random numbers. It's not they are independent with each other, the values which are coming in, but the algorithm what it is using is going to repeat the same algorithm on top of the seed. So you are going to get the same sequence every time you run. Now you may wonder, why do I need it? If I know that it is not a purely random number, why do I need it at all? Why should I support the pseudo randomness in the code? The main reason is debugging your code. When you debug your code, you run it once and you want to create a random noise here, random uniform randomness, all that you are going to use. If you do not have a repeatability of what are the values coming into your network or your program, the sequence of values that are coming in, you won't be able to recreate the problem. The problem is, because it is all input is coming in random, the problem that you encounter, suppose you run it and then it bombs somewhere, it gives an exception somewhere. Now you want to recreate the scenario so that you can catch the problem. Maybe you will put some printf here, you will log some values before where it happens, and then you run it again. Now if there is no repeatability of your data, then you will not be even able to recreate the same condition and to create the same exception, and you will never be able to find the problem. So pseudo randomness is important for you to run the code multiple times but it will give you the same set of input. Then without pseudo random you cannot do it. That's why the pseudo randomness is in fact is brought into the scene. And then there are some different Python supports a global run seed and then a local run. Where is it? I mentioned it. Yeah, global and then random seed, which is the same as a global seed across different versions and tools libraries. Okay, now there are two things here. Okay, when you use set seed, you are actually setting the global random number. Okay, and then one more is, what is the name of that? I forgot. Different versions of library. Operation level. Okay, operation level seed is another one. Now this random dot seed is operation level seed, and global set seed is the global level seed, random seed. Okay, there are two seeds there. Now what is the difference between them? Now I mentioned that you have you have the repeatability. That's the reason we are having the pseudo randomness. Now what if you are using a maybe numpy version 2.32 something, and then you have another numpy version, okay, in the next run or some other build of your program, it is 2.12.1. Now what happens? You want to actually, suppose you want to release your code on this numpy version as well as on this numpy version, then you want to test it out. Your test cases are there, output cases are there, you want to test it out. Now problem is, when you move your application to the another set of tools, okay, I'm not talking about TF1 here and TF2 here, maybe that also you can do if you change the code accordingly for using the library, but it could be a Keras library or maybe NumPy library or some different library, different versions you may be using, but your application has to run on different environments, but you want to test it out on all the environment, then it is better to have a seed which is common across the different versions of the tool, so that you can test it out on all of them and the behavior will be same, and you can compare, because if you want to automate your test cases, all your output should also be compared with the predefined values. You cannot do that until otherwise you have fixed the inputs randomness, and if you change the version of the tool, if the randomness is changing, then your all test cases will be broken. Now you have to have a next set of test cases for running your code on the different version. So that's all, lots of headache. That's why they have given a two seed. If you give them the both the seed and if you set it, that means your code is going to be, across it is going to be the same set of data. Okay, fine. Now you have a random function uniform distribution of values between 0 to 2 pi or 1000 samples. So you are having to have a x values which is going to be in the increasing order. So we want to shuffle it so that it becomes random. Now all these operations based on the seed. Okay, when you do next time, it will do the same kind of a shuffling and it will generate the same set of output. Shuffling will be same, so the same set of data will be there. Maybe you can test it out. I have not done it, but you can test it out. When every run you do, you will get the same values. That is because you are setting both the seed. If you don't do both the seed, then you will not get on different versions. You will have the consistency won't be there if you don't do this guy, and if you don't do this also, then every run also there will not be consistency. It will be different on every run. So if you want to really test it out for that purpose, you can do, but good practice is to have like this in your debugging environment. But when you go to the production, better to remove it, because in production you don't want this to be there. But be cautious about doing it, because sometimes what happens is when in the field some problem happens, you want to recreate the same issue, there will be difficulties. But security reasons may say that you should not have this as seed, because people can predict your output and then they can attack your software. So it depends on the usage. I won't advise you that you should not have seed or you should have seed. There are both advantages and disadvantages which you should be aware of. Based on the condition or based on the situation, you should use it. I hope it is clear. Now Sine value, we are getting the actual values in the 1000 arrays, 1000 values in a single dimensional array, and then I am plotting it, and then we are adding a noise by multiplying a smaller value to the actual 1000 random samples you are getting. We multiply individually every time when you get a new random value, that is getting added to the one of the values in the y value. So every y is getting multiplied with a different, in this case is it different, yeah, it will be different because it is invoked every time. So every time the np random is called for every thing, or it could be same, we have to check it actually. Otherwise you have to do it in a different way. For loop you have to put and then call it once, take the value and then multiply it, so that it will be different. Okay, in this case it will be like a, once it is called and multiplied, it will be a single value. That's why you see the my signal value is like this. Same noise is added, it is not distributed around, because it is called only once and then it is broadcasting is done. Okay, this value is broadcast into the 1000 values, so we have to verify it. Okay, I need to check it out. Okay, fine. Now what you do, you have done some randomness and then you got some x values and y values. X values we have given from 0 to 2 pi, and we have created a y value for each of them and added some noise. Then we are splitting it into two sessions, for training purpose and then for testing purpose. So we are taking a 60% of the sample, that means 600 samples we are doing for training. That means whatever we have 1000 samples, we have 600 are used for training the network, and then we have a test split. That means the remaining will go into the validation portion. Testing is for after doing the training, we do the testing of those with the 200 input. So that is how we compute the metrics and the error. So what we do, 1000 samples we have, okay, with a random noise, okay, x values you have, and then you also have a equivalent y values which are actual values. Then we train it with the 600 samples and then test the network with the 200 samples. Another 200 samples we do a validation. That means validation is done after the testing is done. We will not modify the network anytime during the validation, and we find the how perfect the model is in the validation data. Now if you see that all this one important thing, okay, testing and validation as well as the training input, they all have all parts of the data. That means this is the data, okay, from 0 to 2 pi. All of them should have some sample from each of the values. Is it guaranteed? It is guaranteed by the shuffle that we did in the beginning. Okay, after we generated the sequence of data from 0 to 2 pi, 1000 samples we got, and then we did a shuffle. That shuffle has mixed up the values. So some value here, some here, and then it is all shuffled out, and then we got the sequences of data which is shuffled from the sine wave. Okay, it's not that we are training the network by giving one input like this. Okay, we give one input here, we give another input here, and we give here and we give here. So that is the best way to train a network, when the network is exposed to a different set of input and different values of output. It is not that you give it like this sequentially and train it. It is not going to be trained properly. That's why in your early stages, in the from 0 to 10, okay, not first class to 10th class, you are exposed to all the subjects, different subjects, and then as you come specialization, PhD, then go into postdoc, you just only concentrate on one part of it. But initial stages you are supposed to be exposed to all the things, so that you learn everything, something about everything. That is what we are doing it with the training network also. We want to give the feel of all the input to the network in the beginning stages itself, so that the weights and the biases are modified properly. This is similar to this what I said about jumping. When the inputs are changing, we are actually giving it the different values, so that the weights are actually getting modified in a better way. Okay, they are getting exposed to different values, and they know in a priori that, okay, I need to generate a negative value also, I need to generate a positive value also. So it understands the sine wave. Please remember, the network is learning something without knowing what it is supposed to do. And even after training, you will not know which part of the weight or which part of the bias is actually have understood the sine wave. It is similar to our brain. Which part of our brain or neuron is actually knows something, we don't know. Similarly, in a network, we don't know what those parameters are, which is corresponding to what. It's very difficult to find out. That is the reason. Actually, we want to make it learn by giving different input. That's why this step is very important. Shuffle is very important for your network to converge properly. Okay, have a, question everything why we are doing it, then you will have answers for it. So finally, we are creating an assert to make sure that training size, validation size, and test size all should add up to the sample size. So if it is false, it is going to be assert. It's going to be similar to what you see in C. It will terminate the program and stop and come out if this happens to be false. If it is true, it will continue. So assert when it is false, or assert that it is true. Make sure that it is really true, then only go further. So that's why we are saying make sure it is assert. So you should know whether you have to put a equal to or not equal to. Please remember, don't put the other way, and then only erroneous input will go in, and then when suddenly you give a good one, it will fail, because you will not even know that you have made a wrong choice here. So you have to be very careful on assert. What should you put here? Whether you should look for a true or a false. So we plot it, and then ReLU function is nothing but a max of 0, input. Remember, we are giving floating point because we need to do all the things are in float. Okay, all the inside values are all in float. Of course, sine cannot be a integer. Okay, fine. And then Keras sequential, you already seen it. This is also explained. Summary. Okay, summary is done. We printed the value. Now it is actually showing it is in single cell. Okay, everything. Okay, history. This is where actual learning happens. Fit model 1, I am creating it as a model 1, and fit is the function where the training happens. So we give the input as X train. Y train is the actual expected output, and the model will give something else. And then we give epoch, which is 500 times we are doing. Batch size is 16. That means weights are updated once in 16 samples. After 16 samples have gone through the network. And validation is used for, it's not that it is used only at the end, it is done during the training also. Validation data is fed here. Remember one thing, all this are random, and then it is between 0 to 2 pi because of the shuffle that we did in the beginning. Okay, even though we split it into, when we split it, actually we are splitting it in the order. First 600 samples are taken as a training, next 200 are taken as a for testing or validation. So that is sequential, but because of the shuffle, you get a sample of all the input that you want. So finally, history is printed. Value loss is also computed. Where it is computed from the history. Okay, history has all the information. It's like maintained as a dictionary. So you get the loss value, you get the validation loss, you get a separate loss value, and then validation also. So loss value is got because of the loss function that you have defined, and validation is on the validation data. Okay, it's based on the validation data that we give. Fine. Now what else we need? Okay, loss function, we said that it is a MSE. That's all. We didn't give any function here. It is computing the MSE value. Okay, mean square error value. So if you give batch 16, it will take all the 16 output, and then it will do a MSE there. Okay, not that it is going to lose out on the data. It is going to take all the 16 samples, and then the errors are maintained and kept, and then it will do a mean square error of that 16 value. Based on that mean square error value, sampling, training is done, and that is happening 500 times. So you can imagine every data that you give is contributing to the changes happening to the weight and the bias. Only thing is, MSE is computed every batch size, and then epochs will do after the 16 samples have been given to the model and the error is calculated, then once for all the weights and the bias of all the nodes are done. So when it is doing it, it will do for the all the 49 parameters. Fine. Now what do? We I'm printing it. Okay, epoch wise I am printing how much I am getting as a training loss, whether with the epochs the validation loss are going down or not. Okay, and MAE values how they are changing, because I said that it's a metrics, so we can find the history of how really the training has gone through, what has happened, whether you need to modify any parameters, whether can I reduce the number of nodes or can I increase the epoch, all those things you can do. Training date anyway, you have no options to change in this Keras model. And then that's all. So this is what happens. I hope this is clear. Now I will do run all. What happened? There is a
Sir, it
problem.
has to go through 500 epochs, so it will take some time.
No. Output is not coming. Oh, it may be though going on there. Huh? Okay. But I'm printing output every time. It's not running.
Sir, it's running in the left of the block. This symbol is given and there is a star in it. It's processing.
Oh. No, where are you saying?
Sir, left of each block. Left top.
Laptop. What is that?
Left top of the block.
Okay. I
Yeah.
didn't.
Yeah.
Star is there. I didn't see anything running.
So right now the kernel is idle, so nothing is running. So,
Okay.
In my machine, sometimes when I import TensorFlow, it takes time because it's a heavy.
No, that is true. But as soon as yeah. See,
Yes.
now it is running. I think I have to restart the kernel. Okay, this also something happens. Okay, you will note down that this kernel is not there. So you have to select the kernel, and then it starts. I think this is not very stable. Our notebook editor on the Spider is not very stable, but I like it because of the familiarity. I don't know whether you guys like it or not. Okay, you can see that it is fluctuating. The loss is fluctuating, but finally I think it is coming down. Hmm. Okay, so you can see that I don't need to give 500. Okay, it's not improving at all. Okay, loss is within 100, it has stabilized. I don't see any improvement at all from 100 to 500. And then this is an expanded version of it. You can understand how it is done. I don't need to explain. I think you can see the expanded version of the data points here. And then finally we get this, after all this tamasha or explanation for 2 hours, we get a straight line. Now is the question. I want you to try one thing. Okay, I'll tell you the clue. I will not give you a clue. In the model, I will not tell you what you have to change. In the model, I am telling you, you have to change only entry. One entry to make this fellow like a sine wave. What will you do? First of all, which entry you will pick, and what will you do with the entry? Will you increase it, decrease it? What will you do? Anybody can answer. Maybe I will keep the, but okay. Can you tell me what will you do here? Yeah, go ahead.
So instead of taking one input, we can take previous inputs also.
I didn't get you. One input. Oh, see, our network structure, let me explain. I am not asking you to change the network structure, okay? In the sense, okay, let me clarify. I am not asking you to add any new layers. You should not add any new layers, okay? I am putting a restriction to you. But you change one thing in this model to make your prediction better. What will you do and what change you make? Maybe I will keep
Sir, we can increase the number of nodes that we have used.
how much?
We can try and double it and then see if it is starting to basically converge or not.
Okay, so Amra, you have mentioned it there. Okay, let us do that. Okay, let me ask you one more question. If you increase now the node, how many parameters will be there now because of the change? Suppose I am making this 16 to 32. Is the number of parameters, the configurable parameters are increased to another, how much is the will be the parameter? It is right now 16 nodes and then the parameters are saying 49. Now by increasing this from 16 nodes to 32 nodes, how many parameters this will become? 49 will become what? Is it so difficult?
97.
Okay, this will become 32, this will become 32, this will also become 32, right? So how much it is? 96 plus 1, right? Correct, huh? Okay, let us see what the we'll take input from Somroy, then we'll make it 32, pray to God, and then run it. 97, okay? What we calculated is correct. Okay, it's not gone. Okay, 97. So it will going to take more time now, but let us see whether we'll have to wait. I won't let it do. I will keep disturbing it. How is it? Do you see the beauty of our neural network? I don't know how these guys have come up with this idea way back in 1970s itself. Without knowing what it is doing, it is able to predict the sine wave with just 97 parameters. Okay, it's not just 97. It's a good number, but 500 epochs, 97 parameters are modified with a simple mathematics, just a gradient calculation and MSE error. It is able to predict, given a x, what the y for a sine wave. This is sheer beauty, I would say, and you should appreciate that. Seeing it, believing, and we have seen it. Okay, that's all I have. Any questions before we end?
Sir, I have noticed that in most layers that we create, it's usually the number of nodes is basically 2 raised to the power n of some form. So, what is the reason for that?
Very good question. Okay, let me tell you what it is. I need to tell you something to the hardware. Okay, now finally, whatever you have, the weights and the biases, they are all in the memory, and mostly it will be float. Okay, 32 or maybe 64. Now you see there, this fellow is also powers of 2, right? This is also powers of 2. Of course, the weights and base bias are numbers which are multiplied by the number of nodes, right? So now what is the big question is, okay, this is power of 2, this is power of 2, the size of individual elements, and if you have n number of elements and then you have number of nodes also powers of 2, what you get actually, the total thing what you get is also will be powers of 2. Okay, something. Now still the question would be, why do you need it? Okay, so the reason is the memory hierarchy. We have main memory. Okay, you know that the page sizes are 4 kilobyte or 8 kilobyte. Okay, block sizes or page sizes are like this. You know, Linux has default 4 or 8 kilobyte as a page size. Now what happens in the hard disk, they also store it in segments, sectors, and then lines. They are also in terms of powers of 2. Okay, the way they store in the blocks, they store it in the file, and then when you convert all this model into maybe TensorFlow Lite, and that is also file which is saved as powers of 2. So size is everywhere. If you keep it powers of 2, when you are reading it from there, you will actually happen to cross it in the boundaries of 2. Okay, that's one thing. But when I say it's huge numbers of sizes of 4 kilobyte, 2 kilobyte, you will not appreciate why should I still be bothered about the powers of 2. Now I will come to the next stage, L3 cache. Not what you write in the main memory, what you have it in main memory is running from there. It comes to L3 cache, L2 cache, L1 cache, and then the CPU. Now, how do they come? You may see that L1 cache size normally 32 kilobyte. Okay, let us assume that is a normal. Right now we see 64, 32 kilobyte is that total size of cache. Do not get confused with the total size of the cache, and between that and the block size of the cache is different from the total size. Now what I am talking about is the total size, that's whole size of L1 cache, which is 32 kilobyte. Maybe L2 cache may be 64. I am talking about only data right now. Let us not bother about the code. It could be 128 or 256 kilobyte. Everything is powers of 2. Fine. Now what this is not a big worry. Okay, the block size, the cache size. But what is a big worry is the block size, which could be 32 bytes or 64 bytes, or it could be maybe 128 bytes in terms of bytes. Now what is the block size here? Maybe let me call it as, for example, 32 bytes. What is the block size here? It is certainly more than this, and sometimes it will be multiple of this 32 byte. Okay, let me assume it as 64 bytes, and then block size here is larger, and let me call it as 128 bytes. It could be different for different processors, but we will write like this. Now they are all powers of 2 again. Now you are running the code on the CPU, and it is interested in getting one particular weight W1 from the memory. Assume that this page itself was not there, and then it was brought in from the hard disk, and the whole model is moved into this, and then this weight has to be given to the CPU. It wants it on some AX register, this weight 1. Now to bring weight 1, now this page itself, I said that it has come first on the main memory. It is going to be not there in the cache, because this whole thing came first in the main memory now only. So it needs to be moved up in the memory hierarchy. So what does the memory do? It will cache controller, not memory, cache controller does it remove some block which is already there in the cache, evicts it using one of the eviction algorithm, and then picks out around this value which is aligned. Okay, it is a memory aligned. So alignment is very important when you declare an array. Alignment is important because when the addresses are aligned on 2 byte 2 to the power of values aligned, then the picking up from the memory is faster because CPU memory interface is in terms of either 32 byte address or 64 byte or maybe 128 byte bits, 128 bits wide data bus. So if you are accessing the addresses which are aligned, then it can take all the 32 bytes into the from the memory into the cache or whatever. Okay, so that is also important, alignment of addresses. And when it is reading the value, it will not take from the where it is actually, it will take out from the place where it is aligned to 128 byte, because I said that it is cache is 128 byte size. So 128 byte aligned memory block from the main memory is picked up, which also includes the weight that you are looking for. It comes here, and then your weight is now sitting here. So it will read the 64 byte block here, and again your weight is sitting here, and 32 is read here, and then it goes. So when you are reading the next that W3, it will also be here in 32 bytes. Okay, so if you are having these nodes which are powers of 2, what happens is all the what you create, the weights and bytes and all the blocks will also be in the powers of 2, and it will enhance the way the caches are accessing them, and you are going to have less number of cache misses compared to if you have designed it in a random number. So this is the reason, if somebody asks you why do you have to decide the number of blocks, if you go into the cache, provided if some counter questions comes, you are able to answer it. Otherwise you may get caught somewhere because interview is coming close by. Normally what we do is, the students, when they say something, we latch on to that and go further deep into that, and they go as deep as possible until you say no or you give up somewhere. But don't bluff too much and continue further. Where you have to stop, you have to stop, because honesty is more important in the industry and anywhere. So they will go deeper into digger and see how long they can take you there. So that is why normally questions are asked. Please read more about this if you are very excited about this, and go prepared with that. Then you will have a better hit rate, not a miss rate in the like a cache. I hope this is clear.